So here we have another energy balance problem. And this one, we're going to have velocities changing and MGH changing, some springs. Another unique thing, we will have rotation around a fixed axis where it's not rotating around the center of mass. So this will go into how you deal with inertia of objects when we're not going around the center of mass. So that'll be another new component for this example. Work and energy. There's a couple of different ways that we can write this equation. One is the traditional way where work is just the generic FDS and md theta. If there's no friction forces in the system, so we're not losing energy to heat or something like that, and this work term could be just considered change in potential energy. So rather than saying T plus U equals T, or kinetic energy plus work equals a new kinetic energy, this same equation could be written as potential energy. So you have the initial kinetic and potential energies of the system, and then you have the final kinetic and potential energies of the system. And these two are exactly the same equation. You're just defining that FDS as maybe MGH, or kx dx goes to 1/2 kx squared. So it's the same thing. You're just thinking of everything in terms of potential energy instead of thinking of it in terms of work. Okay, so what do we have here? We have a 30-pound slender rod. Keep in mind this is weight, not mass. And it is pivoting around the point O. So we have fixed axis rotation, and it's not rotating around the center. See, we have a 5-foot long, so if it was at 2.5 feet, that would be rotating around the center. Versus what it's actually doing is it's over here, kind of this random position. So how are we going to deal with like these inertia terms when it's not rotating around the center? So we'll go through a little bit of that with the parallel axis theorem. Okay, the other end is pressed against a spring. K equals 1,800 pounds per inch. And the spring is initially compressed 1 inch. So this is giving us, whenever you see a spring in a problem, your mind should immediately go to potential energy. Okay, the rod is released from this position. Find the angular velocity and the reaction at the pivot as the rod passes through the vertical position. So this is interesting. It's asking for more than just velocity here. It's asking for velocity and forces, the reaction at the pivot. So there's some X and Y forces going on here. As it pops up, so it's going to be standing straight up, it passes through the vertical position. So this is going to combine both our energy balance, and anytime it asks for a force, we're going to have to get back to chapter 16 force balance methodologies. So let's go ahead and get started with the energy. And we'll think of this in terms of an energy balance problem because there's no friction to it. Okay, so initial and final energies, what's the potential energy, what's the kinetic energy? And then once we find those velocities, that will go into our force balance because remember for rotational motion, you have that tangential and normal acceleration, v squared over r, it's velocity dependent. So once you figure out velocities from your energy balance, you can plug those velocities into your force balance, moment balance too. Okay, so we're going to have some force balance, moments balance in addition to energy. So we're mixing strategies here for this one. It's always a good idea to draw diagrams. Draw the initial state, the initial energies, draw the final state, the final energies, and then think about any kind of force or potential energies that are changing from one state to another. And then walk through each piece of this. Okay, so if we look at the initial energy, initial potential energy as well as kinetic energy. So let's start with potential energy. That's this V stands for potential energy. And there's two different energies here. So we have MGH, which let's go ahead and call our datum this 0 point right here. So starting out, we'll have a 0 mgh, so that's our gravitational potential energy. And then at the end, we'll have to look at the new potential energy, and that mgh, the h will be defined by where the center of gravity of this object is. So that was, I think they said it was 5 feet long. So 2.5 feet is the middle of it, but then it's pivoting 1 foot over. So instead of 2.5 feet, we get that 1.5 foot height on there. So pay attention to all the dimensions and things they give you. So here's the starting potential energy. We're starting on the ground, so no mgh. And we have this elastic 1/2 kx squared for the spring. And again, this could be considered potential energy, or you could say, oh, the spring, that's kx dx. And the dx happens from 0 to 1, and you integrate it, you get the 1/2 kx squared. So work through a distance or potential energy, either one, it's turning into the same relationship. Okay, that potential energy changes. So state 2, this is where it's standing straight up on end. So it's not, the center of mass is not at the ground anymore. It is 1.5 feet in the air. So here's our gravitational force, mg. So we use the whole weight, 30 pounds of it. And then our height is 1.5 feet. And in this case, there's no springs. That piece of the problem is done. So we're left with just our mgh. So you put V1 and V2 together, and you can kind of think of how that would look in this original work and energy scenario. So in the original scenario, these are both kind of force through a distance calculations. And you have mgh working force through a distance, and you also have a spring, 1/2 kx squared, working through that shorter distance. So whichever way you want to think of it is completely fine. The V2, if I move this over to the other side, that would be slowing it down. The spring is speeding it up. Okay, from potential energies to kinetic energies. So we'll say that this system starts from rest. So our initial 1/2 mv squared, 1/2 pi omega squared, all that initial kinetic energy is 0. At the end, so we'll say it pops up and it still has maybe some velocity. We don't know what that is yet. We don't even know if it makes it to the top yet. So if you solve for this and you need like a negative velocity or something, then you know, oh, that spring wasn't strong enough to pop it to the top. Okay, so we have the final condition, and this is where fixed axis rotation comes in. So you have to really think about how you're going to include your moment of inertia. So it's not rotating around the center of mass anymore. And so we have to add in 2 terms here, because if you look up inertia in the tables, okay, so you can get like a rod going around the very end, but this is not rotating around the very end. Or you can get the inertia of a rod through the center, and this is what we're going to have to go off of, is the inertia around the center, but then we're going to have to add in this extra 1/2 mv squared of the center also moving, as well as the inertia around the center, because we don't have the inertia around this point of rotation. So kind of 2 pieces for that kinetic energy. So we have the inertia around the center that you can look up on the tables, 1/12 ml squared. So again, here's that table, 1/12 ml squared. These tables, you can get these in Wikipedia or the cover of your book, or just Google moment of inertia of a rod, right? So you plug in the mass, make sure it's mass, not weight. There's the length of the entire thing. And then when you add this 1/2 mv squared, where this is the velocity of the center of gravity of your rod. So those 2 added together will give you the total kinetic energy of it. So again, we have 1/2 m, so not weight, mass. And for velocity, since we have omega here, the angular velocity, it would be good to get both of those velocities into the same format. So V is equal to R omega. So we're using from the axis of rotation up to where the center of mass is. And the velocity of the center of mass is going to be equal to this 1.5 feet times the angular velocity of the thing. So we'll switch that velocity out to 1.5 omega squared. So here's the 1/2 mv squared, 1/2 I omega squared. Plug those both through, and we have a final kinetic energy that is a function of the angular velocity that we can plug into this equation up here. Okay, so plugging in all of our numbers, we can solve for the final rotation. And then once we have that final rotation from our energy balance, so T1, V1, T2, V2, and we just plug all those in there, now we can figure out the forces going on. For forces, always draw diagrams. So we have free body diagram to kinetic diagram. So forces acting on it, and it's not static. They don't add to zero. It's all lopsided. So what it adds to is any kind of x direction, y direction, ma, and I alpha. So here is our moment balance. And you can take the moment around any point that you want on this object, but generally it's going to be easier to solve for it if you look at where all of your unknowns are and take the moment around that point. So taking the moment around this pin here at 0, at O, that means that our x and our y will not be in that moment equation, so it just kind of simplifies it. So taking the moment around O, 0 on this side. So like mg just acts straight through that point. There's nothing that's actually trying to rotate it around O at the very end of it. So 0 is equal to, and you have to do the same thing on both sides of these, free body diagram or kinetic. So we're looking at the moment around 0 hit here again, and you have some kind of a radius and max. You have to get the perpendicular piece of it. That tangential piece of it, remember that's going to be the R alpha. You're looking for the 90-degree relationship there. So there's our R cross MA, and we're going to also add in I alpha, where that's the inertia around the center of mass of it. So there's our moment balance, and here's our forces. So everything in the x direction. So at this little pin, there's going to be some force in the x direction, and that reaction is going to be equivalent to any kind of angular acceleration that happens to be happening in the x direction. So Rx equals ma, where a is equal to this R alpha tangential piece of your acceleration. In the y direction, so if I look over here, I have mg acting down, and that is held up by this pin pushing up. So we have the pin pushing up minus the weight acting down, and its dynamics, if it's moving, these are not equal and opposite. They would be equal, excuse me, they're going to be equal to the normal piece of our acceleration. So this is the acceleration in the y direction. We're doing the forces and everything in the y direction, r omega squared. And that omega squared is something we got from our energy balance equation. So here we go, the forces in the y direction, forces in x direction, moments. We have 3 equations, and we can solve for 3 unknowns, our x, our y, and alpha. And it turns out at the very top, there's actually no acceleration going on in that direction. There's no forces in that direction, so that makes sense. That alpha and our x are 0 because there's no real external x forces. And all we have is this reaction in the y direction. It's caused by the velocity that's happening up here. So because of that velocity, you have r omega squared or v squared over r, which means that r is not equal and opposite to the weight anymore. So that's a good mixture of energy balance, looking at energy versus work and energy, how those are the same things, and also mixing that in with a force balance as well at